Okay, so again, I just want to double check. Can everyone see my screen and my mouse moving? It should say Module 2, Atomic Structures and Electronic Configurations.
Yes, it's okay.
Okay, great, great. Okay, so the Module 1 focused on how atoms are arranged in solid materials. Okay, so we talked about the crystal structures. We talked about 3D, 2D, and 1D lattices. And so this module is going to talk about the properties of electrons and how electrons are arranged in individual atoms. The reason we're doing this is that it's just this logical approach of the dogma that we talked about last week. And that dogma is that the atomic structure of a material determines the properties. How does it do that? Well, the atomic structure determines something called an electrostatic potential condition. The distribution of atoms and the distribution of nuclei creates something called a potential field. And that potential field determines where the electrons are and how they are oriented. So what we're going to do in this module is we're going to do a simple version of that concept. So we're going to look at how electrons are arranged in individual atoms. So just an atom, a single atom on its own in free space. And so what we'll find is that electrons are located in discrete energy levels. In the next module, we're going to talk about what happens when you, instead of individual atoms, when you have crystals. So you have a whole ton of atoms that are connected in a two-dimensional or three-dimensional lattice. So then the locations and behaviors of the electrons changes compared to just a single atom on its own. Okay, so they form something called energy bands. So again, getting back to the dogma, atomic structure determines electronic properties. So the atomic structure determines the electronic configuration. That's why this module is called electronic configurations. And electronic configurations basically refers to how the electrons are organized in the atom, like residing in certain energy levels or orbitals and things like that we'll talk about. What are the energy states that they reside in? That's the electronic configuration. And the electronic configuration determines the electronic properties of the material. That's why we're interested in this. So this is going to include some concepts from electronics. It's going to include some concepts from, I borrowed a book on modern physics that gave some explanations on the different phenomena that relate to quantum mechanics that we'll touch on this module. This is not a class in quantum mechanics, so I can't say that we're going to be able to go into all the details of quantum mechanics and all the beautiful theories that go around there. We're just going to touch on enough so that you can know how semiconductor devices work. So it's a little bit more focused in that sense. Okay, so what is electricity? I'm mentioning this here because it gives a motivation for what we're learning in these modules. Ultimately, what we care about is a transistor that's switched on and off, a bipolar junction device that's switched on and off, and we want to know how current is flowing through the device. So let's just start with the definition of what electric current is. It's the movement of charges. Okay? If you have charges that are just sitting on their own, that are not moving, that's not electric current. The charges must be moving. All right. There's two types of charges in semiconductor devices. There's electrons and then there's holes. We've talked about electrons already. Does anyone remember what holes are? I just want to get a sense.
Positive charged ions.
Okay, that's Sri?
Yeah, Sri here, sorry.
Thank you, Sri. No problem. Sri said positively charged ions, but very close, very close. They're positively charged particles. Ions are considered things that are in liquid, like things that like salt and salt and that would be considered a salt. They dissolve and they form like positive and negatively charged particles that move through liquids. So I think holes would be better described as just a positively charged particle. And what holes are is actually the absence of electrons. Whenever there's no, wherever places there's not an electron, the absence of an electron is referred to as a hole. We'll talk more about that in the next module. Don't worry about that yet. So to find the electrical behavior of a material, we want to know where these charges are located, and we're going to focus on electrons right now. We'll get into holes later. To find the electrical behavior of a material, we want to know where the electrons are located, how much energy they have. That's the electronic configuration. That's module 2. We also want to know how many electrons we have. That's carrier concentration. That's module 3. The reason we want to know how many electrons we have is because electric current is a movement of charge. The more charges you have, the higher the concentration of charges, the more current you'll get. So we are interested in the concentration of electrons and holes as well. We're also interested in how they move and how fast they move. So we'll talk about drift and diffusion currents. Those are two mechanisms by which charges move, and we'll talk about that in modules 2, 3, and 4. A little bit in this module, but mostly on 3 and 4. So module 2, right now, we're just focused on where the electrons are located and how much energy they have. So we're going to talk about things like orbitals and energy levels and so forth. Okay, so let's start with a sort of a historic perspective, because it seems like physics books, they always tend to give a historical perspective or the scientist perspective. So I think this is something that we can all appreciate. Look at this from the perspective of a scientist. You see an interesting effect like this. I'm sure you all have seen these types of signs in like stores or restaurants or things like that, where you have a tube that's filled with gas and then it lights up different colors. They call them neon signs, plasma tubes. And the different gases, they glow different colors. Have any of you seen signs like this anymore? I know that a lot of these have been replaced with LED signs, but have any of you seen like neon signs?
Yeah, it's like the classic open or closed sign in the store. This is David.
Yeah, that's right. The classic open and closed sign, exactly. So how these things work is that there's a tube that has been, the air has been removed, and what they do is they fill it up with a certain gas instead. And what you notice is that every gas glows a different color. Helium and neon and argon and krypton, and they all have a different color that they glow. And if we were to look at it closely, if we were to put this through an instrument called a spectrometer, let me just remind everyone what a spectrometer is. Just do a quick image on that. Find. Yeah, this is an example of a simple spectrometer. Let's zoom in here. So you have a light source, and the light source may contain many different colors, okay? So the light source may contain many different colors. It hits something called the diffraction grating. You can also use something called a monochromator, but let's just say you use a diffraction grating, and what the diffraction grating does, it splits up the light into different colors, like the violet light bounces off in a certain angle, and the red light bounces off at a different angle. So it basically splits up all the colors that were part of this incoming light. Okay, just don't worry about the rest of this right now. This is the most important thing. They use spectrometers, and what spectroscopists found is that when they looked at the spectra, they would see a whole bunch of different lines here. Okay, a whole bunch of different lines means, let's zoom in here. A whole bunch of different lines here means that there are many different colors being given off by that plasma tube. All right, a combination of different colors. And what they notice is that the lines, which each line consists of a single color that's being given off, there's multiple lines, so each plasma tube gives off many different colors. But they're always the spacing between them always followed this very unique pattern. And so spectroscopists looked at that and said, like, why is there just a unique pattern like this? There's a very fixed spacing between them. And it's not just like, you're not seeing all colors of the spectrum, you're only seeing very specific colors of the spectrum. And so that was in the late 1800s. Spectroscopists noticed that this was happening. And but this was a very important experiment because Niels Bohr looked at this, and also people like Planck looked at this, and they used this to figure out a few important things. Number one is that light is given off in discrete quanta that are called photons, and those photons have specific wavelengths. The second thing they found was that, the second thing, which I'll talk about in the next slide, is the Bohr model. It actually helped determine a model of the atom. Okay, so they were looking at these spectra, and they saw that helium had a certain spectra, a certain pattern of lines, and then krypton had a different one, argon had another one, neon had another one, right? So Niels Bohr, in 1913, he came up with a model of the atom to help explain this phenomenon that he saw. So what the Bohr's model is really elegant, and it helped explain these things, because basically he said that he claimed that this light that was being given off, okay, lights of different wavelengths were being given off, they corresponded to energy transitions in the atom. And that was the really big contribution that Niels Bohr made to modern physics. So he said that, like, when an electron goes from a high energy state to a low energy state, it gives off a photon of light. And the amount of the difference in energy between the two states determines the energy of the photon, and the energy of the photon in turn is related to its frequency or its wavelength. Okay, let me just add something here, just so I want to make sure that everyone knows that frequency is remind everyone that the frequency of light is also related to the wavelength. Frequency equals, hold on. Frequency and wavelength are related by this relationship here. All right. All right. Can everyone still hear me? Can everyone still see this slide?
Yes.
Okay, great. All right, so here's the Bohr model of the atom. Okay, so he said that his model of the atom was that electrons orbit the atom in discrete energy levels. Okay, and these energy levels he denoted by this bold letter N. And so low energy electrons orbited in smaller radii, higher energy electrons orbited in higher energy states, so which had a larger radius. High energy electrons have a larger radius, so that radius is Rn, and they also have a larger velocity, v. And the specific relations are actually right here. And with these equations, you can actually do some simple calculations of what the radius is and what the velocity is, and what the difference in energies are between two different states. So you'll probably have some homework problems on this, and I hope that you'll see that these it's not terribly difficult to do. It looks like some weird equations here, but the calculations are actually pretty easy to do. So the other part of the Bohr model said that there's energy transitions. So if an electron is excited some way, all right, in these neon signs, they're excited by a discharge, meaning you run an electric current through the gas and you excite the electrons that way. So they're using electric discharges here. So with the electric discharge, an electron jumps from a ground state to an excited state. So let's say it transitions from energy level 1 to energy level 3. Okay, and then after some time, it falls back to the original energy level. Okay, and when so the reason it went up to a higher energy level is because it absorbed energy. Some energy was required to make the electron go from a low energy state to a higher energy state. Now, when the electron goes from the high energy state to the low energy state, that energy has to go somewhere. It can't just disappear. So when the electron goes from a high energy to low energy state, that extra energy, the difference in energy, is given off as a photon of light. Okay, a photon is a single packet of light, a single quanta of light. Okay, and this was a big advance in modern physics. This whole idea of light being in the form of quanta. We'll talk more about like the wave nature and the particle nature of light as we go. But the main thing from the Bohr model is that the energy and the frequency of the photon that's emitted is proportional to the difference in energy. So it's E2 minus E1. And you have formulas for all this stuff that you can basically figure out the wavelength of the photon for these different energy transitions. So the energy transitions that end at energy level 1 is called the Lyman series, and then the ones that end at 2 is called the Balmer series, and the ones that end at energy level 3 is called the Paschen series. So you see that a particular atom will have a series of energy transitions. This slide is showing the Bohr's model. How does Bohr's model explain the atomic spectra? His model of hydrogen says that there's a bunch of different possible energy transitions. Okay, and there's a finite number of them. Okay, the differences in energy, they're very discrete changes in energy. Okay, you can't just have a random a quanta of light, because you don't have every possible energy. You only have these possible energy transitions. So that's what results in these discrete lines in the spectra. Discrete lines in the spectra corresponds to discrete energy transitions in the atom. And that's how Bohr and Einstein and all those guys said that, oh, you know, like the electrons must be in discrete energy states in the atom. So the Bohr model was a big advance, and it works well for hydrogen, but for complex atoms, for more complex atoms, the Bohr model actually breaks down, and the atomic spectra don't always correspond to the Bohr's model. But it works very well for simple atoms, and it greatly advanced our understanding of the discrete nature of spectra and just the discrete nature of electronic configurations in atoms. Electrons can exist in discrete energy states only. Okay, good. So now we can talk about another important concept. It looks like we have about 10 minutes left here. A very important concept in modern physics is wave-particle duality. So we found out from here that light is being given off in quanta. Okay, so in that sense, light is behaving as a particle, but that particle has a certain wavelength associated with it. So that is an example of light exhibiting wave-like properties and particle-like properties. I'll show another example of that on the next slide. So electrons, neutrons, and other particles also exhibit similar behavior, meaning that they can exist, they exhibit some properties that are wave-like and some properties that are particle-like. And so things, physical phenomena or observations or experiments that scientists do which show that the wave nature of light are things like interference, diffraction, polarization, refraction of light in lenses. Those are all things that waves do. And there's other effects like the photoelectric effect and some things about reflection and refraction, splitting atoms. Those properties exhibit the particle nature of light. And as I mentioned, this wave-particle duality also exists with electrons and neutrons and other particles. So just to have some concrete examples so that you can hang your head on this idea. An example of a wave-like behavior would be diffraction patterns. So this is an example, a simple example that I took of photon diffraction or light diffraction, the classic single slit experiment. Have any of you done these experiments in your physics class? Does anyone remember doing an experiment like this in a high school physics class or college physics class?
Yeah, I did the single slit experiment.
Oh, excellent, excellent. And who is this?
Yeah, this was Jake Marova.
Okay, great. So did you guys use a laser?
I believe we did, yeah.
Okay. Yeah, you use a laser and then you have like a sheet or piece of plastic that has a really, really tiny hole in it. And that hole is in the micrometer range or the nanometer range. What happens in this experiment, there's also a double slit experiment that's also, it might even be more popular than the single slit one. But this experiment, it shows that light behaves as a wave. So an example of what waves do is that there's constructive and destructive interference. I'm going to zoom in here so you can see, like, this is an example of constructive interference. If you were to take a wave, the wave number 1 and wave number 2, and add them together, you would get a wave that has a larger amplitude. That's an example of constructive interference. If, on the other hand, you were to take two waves like this, and they were out of phase, this is just showing like 180 degrees out of phase. So whenever wave 3 has a high value, wave 4 has a low value. So when you add these up, the result is you'll get a 0. If you add these two functions up, you'll get a 0. So as a result, what happens in this single slit experiment, what's interesting is that this plane wave that's coming in can actually be thought of as a whole bunch of different point sources of light. And so one point source generates a wave at each one of these, wherever you see these arrows, it's a point source for light. And those point sources go in all different directions. But in certain places on the paper, let's say you put a paper here and you look at the interference pattern, on certain places on that paper, these waves from the point sources are going to constructively interfere, and so you'll get a very strong light pattern there. And in other places, the waves will destructively interfere, like in here, and these places you'll get a dark region. So you'll have regions of, it'll be very bright in the middle, and then it'll go dark, it'll become bright again, it'll go dark again, and so forth. It'll be in a periodic pattern. And that periodic pattern can actually, it's related to the slit dimension, and it's related to the wavelength of the wave, and so on. But if light behaved purely as a particle, what do you think this pattern would look like?
It would be just a big lump in the middle.
Exactly. If light were behaving as a particle, it would just be a lump in the middle like this. If you didn't have constructive and destructive interference, these photons would just, if this is purely a particle thing, the particles would go right through like this, they'd hit the paper, and then you'd see some light on the paper here. But because of constructive and destructive interference, you see this diffraction pattern. So this is an example of light behaving as a wave, or photons behaving as a wave. There's also examples of electrons behaving as a wave. We're going to talk about in this chapter that electrons also have wave-like properties, but the wavelength is very, very, very small. And so you can do really cool stuff with electrons in terms of imaging and looking at crystal structures. So the way that I'll explain this for now is that, this slit, in this photon experiment, this slit was on the order, you try to make it very small, you try to make it on the order of the wavelength of the incoming radiation, so the wavelength of the photons. And the wavelength of the photons can be in the, in the micron range if it's infrared, or hundreds of nanometers if it's in the visible range. But with electrons have a super small wavelength associated with them, especially high energy electrons. And so the slit can actually be the spaces between atoms in a crystal, which is quite amazing. So if you put electrons through a crystal lattice, they will actually form, the slits will actually cause diffraction patterns. The slits being the spaces between the atoms, they'll form diffraction patterns on a two-dimensional grid like this. You can look at where the electrons constructively and destructively interfere. The bright zones are where the electrons constructively interfere, and the dark zones are where they don't. Based on this diffraction pattern, you can actually estimate the spacing between atoms and really cool stuff like that. So this is the electron diffraction pattern from this crystal, which I don't know how to pronounce the name of this, but the point is that this is a diffraction pattern. This is showing where electrons have a wave-like behavior. Now there are examples of particles exhibiting particle-like behavior. This is an example of light photons exhibiting particle-like behavior, and this is called the photoelectric effect. This earned Einstein the Nobel Prize in 1921, where he showed this effect, and he showed how this effect shows the quantized nature of atoms. All right, so let's talk about how this, why this shows that particle-like behavior. The way this is often described is like billiard balls. Okay, you have light coming in here, light or photons. If you just imagine this as a stream of photons, like little ping pong balls or billiard balls, knocking into this metal material. And this metal is held under vacuum. Okay. The reason why it's held under vacuum, it's a subtle point, but when the electron bounces off, you don't want the electron to recombine with other, like, air molecules. Okay, so it's done in vacuum. The light, think about this as a stream of photons, like billiard balls, a stream of billiard balls, like hitting the metal. And when you hit it with enough energy, it actually removes electrons from the metal. So in some sense, the electron is also behaving as a particle here. The photon is behaving as a particle. The electron is also behaving as a particle. It's kind of like this billiard ball-like effect. So he used metal, because metals have this thing called a work function. Let me just put this into context here with the Bohr model. So we go back to the Bohr model here. Uh-oh. So in the Bohr model, can everyone still hear me?
We can hear, but I cannot see anything.
The PowerPoint's not responding. Okay. Just restart that. Okay, so if you imagine that the atom has certain energy states like this, if you supply enough energy to the electron, it should be removed from the atom completely. Instead, it goes to the highest energy state, and when there is no more energy states within the atom, it leaves the atom completely, and that's what's happening here with the photoelectric effect. So the electrons are getting knocked off. Photons knock out the metal as if the photon has sufficiently high energy. So this is an important point of Einstein's work, was that he was changing the energy of the light. He was basically, the energy is equal to Planck's constant times the frequency, as I showed you earlier in the earlier slide. So he was using high frequency light, like ultraviolet light, and he saw that low energy light did not eject the electron, and high energy light does eject the electron. So the minimum amount of energy that he needed in order to eject electrons was equal to Q times 5, which is the metal work function. Okay, So imagine that you're tuning the energy of your light source. You're basically bumping up the energy, and that's this is the frequency of the light. Please don't be confused by this V. Just the V is equivalent to F here. Okay, so as you increase F, you're also increasing the energy of the light. If you use really low energy light, the electrons are not getting knocked off. Once you get to a point equal to Q times phi, once the energy is equal to Q times phi, then you have enough energy to knock electrons off. And as you increase the energy further than that, then the ejected electron has more and more energy. So it's like if you throw a billiard ball really fast at another ball, then when the energy is transferred to that other particle, the second billiard ball is going to go faster. So the faster you throw it, the faster the deflected particle will move. All right. So the kinetic energy of the ejected electrons increases with the energy of light that you put into the system. Okay. So this is an example of a particle-like behavior. Okay. So I think this is a good stopping point. We're at 7:10 right now. So we're going to start next week on the de Broglie wavelength. From the de Broglie wavelength, we'll talk about photons versus electrons, and then we're going to get into the Heisenberg uncertainty principle, probability density functions, and then finally we'll get into the Schrodinger equation. And the Schrodinger equation is what ultimately tells us things like this. It tells us what the orbitals look like. The electrons reside in these things called orbitals. You'll find out about that next time. And then also about electronic configurations. We'll talk about these band diagrams, and we'll talk about these energy states like the 1s, 2s, 3s energy states and what they look like in silicon. All right, so we'll stop there now. Please check your email, because I do expect to upload some kind of homework in the next week or so. So stay on the lookout for that, so you can get some practice on the problems. And Monday's class will be at the regularly scheduled class time. It'll be it won't be an online lecture. It'll be right in class. Okay. So quick feedback: did this format work for everyone?
I thought it was good.
Pretty well.
Okay, good. So let me know. Feel free to email me privately. Let me know your feedback if you have any issues with it. If everyone's okay with it, you can let me know that too. And this is just because I'm just thinking like how we're going to handle like some of the future lectures when I'm not in town. Okay. All right. Thanks a lot for your time. So what I'm going to do here is I'm going to stop the recording here, and I'll see you all next week.
Thank you, Professor.
Thank you.
Thank you.